In this video, we're going to look at another type of word problem that involves solving a differential equation and applying separation of variables. According to Newton's law, the force of gravity on an object of mass m that has been projected vertically upwards is inversely proportional to the square of the distance from the center of the Earth, and is given by f of y is equal to minus k divided by y plus r squared. K is a constant. So y equals y of t is the object's distance above the surface of the Earth. G is the acceleration due to gravity, and r is the radius of Earth. Part A of the question asks us to show that mass times acceleration, m dv dt, is equal to minus mg r squared divided by y plus r all squared. Part B of the question, a rocket is fired vertically upwards with an initial velocity v0. Let h be the maximum height above the Earth's surface. Find the initial velocity for rocket to reach a height of h. We need to apply the chain rule. Mass dv dt is equal to mv dv dy. So we have to apply the chain rule to produce that result. Part C. Find the escape velocity ve such that the rocket does not return to Earth. And part D of the question gives us some values for radius. So this is the radius of the Earth, 6371 kilometers, and gravity on Earth is 9.8 meters per second squared. And we're asked to find the escape velocity in meters per second and also in kilometers per hour. All right, let's get started with part A. So for part A of the question, we would like to show that mass times dv dt is equal to minus mg r squared divided by y plus r all squared. All right, so we know that f of y is equal to the force of gravity between the object and Earth is minus k divided by y plus r all squared. But at the Earth's surface, when y equals 0, the force of gravity is downwards pointing towards the center of the Earth, and it's equal to minus mg. That means when y equals 0, the force is negative mg. This allows us to solve for k. So we get minus mg is equal to minus k divided by, and y equals 0, so we get r squared in the denominator. And if we solve for k, cross multiply, we get k is equal to mg times r squared. So f of y is equal to minus mg r squared divided by y plus r all squared. Now we know force is mass times acceleration. That's Newton's law. So force is equal to mass times acceleration. And this is equal to mass times dv dt. Acceleration is rate of change of velocity with respect to time. And this is equal to minus mg r squared divided by y plus r all squared. And this was the result that we were trying to prove. So mass times acceleration dv dt is equal to minus mg r squared divided by y plus r all squared. Part A of the question is done. All right, let's look at part B. Part B asks us to find the initial velocity for the rocket to reach a maximum height of h. So by the chain rule, we know that dv dt is equal to dv dy, rate of change of velocity with respect to height, times dy dt. But dy dt is simply velocity v. So we can rewrite this as v times dv dy. So we have mass times dv dt is equal to mass times velocity times dv dy. And this is equal to minus mg r squared divided by y plus r all squared. So that's our differential equation. Of course, mass cancels out, so let's cancel that out. And what we get is v dv dy is equal to minus g r squared divided by y plus r all squared. So this is a differential equation. Let's separate the variables, multiply both sides by dy, and we get v dv is equal to minus g r squared, multiplying both sides by dy, divided by y plus r all squared, multiplied by dy. Alright, so now the next step is to integrate both sides. So integrate the left-hand side with respect to v, which is velocity, and integrate the right-hand side with respect to y, which is height. Alright, so let's do that. We have integral v dv is equal to integral minus g r squared divided by y plus r all squared dy. We'll apply U substitution. So let's write this in, U sub. Let U be equal to the inside function, y plus r. Differentiate both sides, and we get du is equal to dy. So on the left-hand side, integrate v dv, we get v squared divided by 2 is equal to minus gr squared is a constant, passes through the integral, and the integral of 1 over y plus r squared dy, applying U substitution, that just gives us 1 over y plus r plus c. Multiply by 2, so we can isolate v squared. We get v squared is equal to minus 2 g r squared. Sorry, there's a little mistake here. When we integrate minus 1 over y plus r squared, we get plus 1 over y plus r. So we don't need this minus sign here. This minus sign is gone. Let's erase this as well. So we get 2g r squared divided by y plus r plus c. Alright, so actually we get 2c. And 2c is just another constant. We'll call it, let's say, c1. Let's write this in. c1 is equal to 2c. And square root both sides so we can solve for velocity. v is equal to plus or minus root of 2g r squared divided by y plus r plus c1. Now, because the rocket is moving up, we expect the velocity to be positive, so we only take the plus square root sign. So v is equal to root of 2g r squared divided by y plus r plus c1. Alright, so what we have is velocity of a rocket is root of 2g r squared divided by y plus r plus c1. So we have velocity as a function of height y. Now we know that y equals 0, the rocket is on the ground when t equals 0. Initially, that is. That's the initial condition at t equals 0. So the velocity as a function of time when t equals 0 is equal to the velocity when y equals 0, when the object is sitting on the surface of the Earth. And this is equal to v naught. That's the initial velocity. So v naught, substitute that for velocity, is equal to root of 2g r squared divided by y equals 0, so we divide by r plus c1. And if we simplify this, we get v naught is equal to, and r squared cancels with r, and we just get r in the numerator, root 2gr plus c1. Now square both sides, we get v naught squared is equal to 2gr plus c1. Now we can solve for the constant. c1 is equal to v naught squared minus 2gr. So we can now build the velocity function as a function of height. Velocity v of y is equal to root of 2g r squared divided by y plus r plus c1. We solve for c1 is equal to plus v naught squared minus 2gr. So we now have the velocity at any height. So if we know the height y, we know the velocity of the rocket. Alright, for part B, Continuing on part B, we want to reach a maximum height of h. So what is the initial velocity that is needed so that a rocket reaches a maximum height of h? So we want a maximum height of h. And the question is, what is the initial velocity of the rocket to achieve that maximum height? What is v naught? Now, when an object reaches maximum height, the velocity becomes 0. So let's make the velocity equal to 0 and the height y is equal to h, and solve for the initial velocity needed to achieve a maximum height of h. So v of y is equal to root of 2g r squared divided by y plus r. Let me write this better, r squared plus v naught squared minus 2gr. So the key concept again is that the maximum height is reached when the velocity is 0. So let's make the velocity 0 and let's make the height is equal to h, and let's solve for the initial velocity needed. Solve for v naught. Alright, so we have 0 is equal to root of 2g r squared. Substituting y equals h, we get h plus r plus v naught squared minus 2gr. Square both sides and we get 0. We get rid of the radical. 0 is equal to 2g r squared divided by h plus r plus v naught squared minus 2gr. Now solve for v naught squared. So v naught squared is equal to 2gr minus 2g r squared divided by h plus r. Take the square root of both sides and solve for the initial velocity needed to reach a maximum height of h. So v naught is equal to root of 2gr minus 2g r squared divided by h plus r. This is the initial velocity needed for the object to reach a maximum height of h. Alright, so now the next part of the question, part C, is to find the escape velocity VE. The escape velocity is such that the rocket does not return back to Earth. Now we solve for the initial velocity needed to reach a certain maximum height. So V naught is equal to root of 2gr minus 2g r squared divided by h plus r. This is the initial velocity needed to reach maximum height h. So to find escape velocity, let's take the limit of the initial velocity, v naught, as the height approaches infinity. This is equal to root of 2gr minus 0. Why is this 0? Because height is going to infinity and height is in the denominator. So the denominator of ratio grows to infinity, so the ratio becomes 0. So we get root 2gr. This is the escape velocity. V escape is equal to root 2gr. And it doesn't depend on the mass of the rocket. It only depends on gravity and the radius of Earth in this case. Alright, so part D asks us to find the escape velocity for a rocket leaving Earth. And we're given that the radius of Earth is equal to 6371 kilometers. And gravity on Earth, G, is equal to 9.8 meters per second squared. So escape velocity, we derive that to be root of 2gr. And this is equal to root of 2 times 9.8 gravity times the radius of Earth, which is 6371. And the escape velocity, if we put this in, what do we get? So actually, we need to change this 6371 because that's kilometers. We need to change it in meters. So let's multiply it by 1,000 because there's 1,000 meters in a kilometer. So we find the escape velocity to be equal to, if we simplify this and decimalize it, we get 11174.6 meters per second. Now, the question also asks us to make a change of units and also get the escape velocity in terms of kilometers per hour. That's pretty easy to do, so let's do that. So escape velocity is approximately equal to 11174.6 meters per second. There are 1,000 meters in a kilometer, so times 1 kilometer divided by 1,000 meters. And there are 3,600 seconds inside an hour, times 3,600 seconds in 1 hour. All right, so the seconds cancels out, and the meters also cancels out, and we get our answer in kilometers per hour. So escape velocity is approximately 40,228.5. So about 40,000 kilometers per hour is escape velocity for this rocket, such that it does not come back to Earth. Now let's summarize what we've done. Here we have a summary diagram. So we have the planet Earth, that's the circle, and the surface of Earth is y equals 0. This is a rocket here of mass m. The force downwards towards the center of the Earth is mgr squared divided by r plus y squared. So we derive this part here, mass times dv dt is equal to minus mgr squared divided by y plus r squared. We apply the chain rule to obtain a different result, to get a differential equation that only involves velocity and height. So in doing that, once we have that differential equation, we separated the variables and we got velocity as a function of height. And then the question was asking us to find the initial velocity needed for the rocket to reach a maximum height of h. So we set v equals 0, y equals h, and we found the initial velocity that was needed for a rocket to reach a maximum height of h. We then went on to take the limit as height goes to infinity of this initial velocity, and that gave us the escape velocity root 2gr. That's the escape velocity for a rocket such that it doesn't come back to Earth. All right, thanks.